Okay. So in your text, we'll try to look at the big picture here. Yeah. Olympic level attempt at the. Here it is. Well, here it is.
Ah.
Short. Okay. That's okay. There will be more. So the class of problems identified as P type problems are those that have polynomial time solutions. That means if we were to add up, say, looking at and we have some and we might have a we could come up with a polynomial representing the total amount of time that this took. And recalling that two nested loops inside of each other have a multiplicative effect. We look at this, so this would be, so the time in terms of n might look like what? Well, how many times is this going to get called total? And squared. So like and then this is counting negatively, but it's still going to go n times, right? So it's like 150 times n, and maybe there's something that happens outside the loop that would just be some kind of a call that's 50 milliseconds, like that. So if we're trying to find the total processing time, just trying to give you the picture of how we come up with the idea of what a upper bound might be when we're using big O notation. So this would be, right, we can get a polynomial that would be like 50 milliseconds. So our total time, we would say, as n changes, our total time is going to be changing according to a polynomial like this. Make sense? So when we actually look at that in a big scale, n is increasing and time, we're referring to processing time. So this would be what happens as n gets large, right? We say we usually stay away from saying as n goes to infinity, right? That's for the math department doesn't have any problem with throwing around infinities like they grew on trees, right? But we'll say just as n gets large, as n gets very large, well before it hits infinity, some of these things are going to start dropping out. So we've got a, this would be like a, what? We multiply that through, right? We got like 3,000, oh, not 3, 2,000 n squared. When n gets to when n gets to 150, what does this term look like? Kind of looks like 150 times 150. So it looks like just an additional n squared, right? So we're talking about n is getting bigger and bigger, right? So kind of, we could, when n is 150 or larger, it kind of starts looking more like a, right, that plus 50. Well, as you're talking about n squareds and 2000s, this little 50 guy starts looking pretty unimportant, right? That little 50 nudges the, this is going to be a parabola, right? And the n squared one is going to be a parabola. And so that little 50, depending on where our scale is, as n's getting big, it's just going to bump it a little bit up, right? But the shape is going to be substantially the same. So all that is kind of my hand waving justification that all we really care about is the highest order power of n. So we're going to drop the coefficients and drop coefficients and lower powers of n. And that's going to be our big O notation. So we've talked about this a little bit already. But now we have the point that if we're looking at powers of n, expressions, functions of n, we've got a curve of this kind of shape. You recognize that as having a basic form.
Log?
Yeah, that's going to be like a log shape, right? Log of n and a linear So, it's supposed to be linear. Okay, more linear. This is okay, log in. But what we're trying to do is recognize the overall shape of the curve, right? What we care about is how fast does the function grow as n increases. So we're trying to characterize the whole point of the big O notation is to characterize the rate of growth for the time factor t of n as n gets really big. So granted, if you're talking about, n's of 1 or 2, then the differences are going to look more significant for small n's, individual calculations. But as n gets large, what the less important features drop out, and even the coefficients drop out, so that we're actually looking at a function is big O, our estimate, our big O is our upper bound, and it is related to f of n if there's some constant that bounds a function. I say the function t of n. So here's our definition. We're basically saying that if there exists two possibly, I mean, you could hit exactly on, but if there exist two constant coefficients that you can apply to this function that is the big O, then we say that it's bounded, and we care most, right? When we're expressing the big O notation, we're saying that it is the upper bound times some coefficient we can stick on the front of the real function. Okay, so if you think about that a little bit, and start considering what this polynomial looks like as n gets really, really big. As n gets big, that n squared, or we use n squared for simplicity, but you could potentially have any number of, my nested for loops could call another function that actually, function with n as its argument, that actually did its own nested loop. So you could have n to the third, n to the fourth, n to the 50th, right? And so what we're saying is we'll take our big O estimate, and you can show this, but basically if you pick, you can get here, the easy way to do that is to pick the highest power of n in this expression, the time calculation. Pick the highest order, highest degree of n as your f of n, then this will be true. So if this has the highest order of n cubed, the closest one, if you make this n cubed, then you can always find a coefficient big enough to apply on the front of n cubed that it'll be greater than, it'll be an upper bound for that actual theta. And so we're coming to a point where as long as you're dealing with simple powers of n, over here, I have, forgive the, and it's supposed to be spending a little bit more, but I'm trying to leave room for my, maybe an n cubed going here. And then there's a multimedia extravaganza here. Everything over on this side can make a, well, wait a minute, what about end of the 20th? What about end of the 50th? It still falls into the tractable function, or tractable set of functions, and which is equivalent to this, right? It's still a polynomial time function if it can be expressed as a power, simple power of n as the big O, as the upper bound. So at some point, we run into the intractable area. And those are the functions like these are and this is going to give rise to your first misconception. These are exponential in growth rate, and so they go well beyond simple polynomial functions. These fall into, here's where you have to learn nothing else. You have to learn what NP actually means. So P means polynomial, and these guys are not polynomial. What does NP obviously mean? That's the correct answer. A common. So this is, if anybody that's ever trying to show off what you learned in automata, then do not mistake NP for not polynomial. Okay. It means non-deterministic polynomial, which is different. Deterministic polynomial. Oh, tear that off there. Okay. An oversimplified answer. Remember what we said about non-deterministic, say, finite automata, NFAs? Remember we said there were a few different ways to think of them, but one of those was that it basically tries all the possibilities until it finds a path if the one exists, right? So when you see non-deterministic polynomial time or type of problem, very often it is try all the possibilities. So as soon as you get into that, another equivalent, I guess, statement. So this is not 100%. If you're looking for a touchstone of when you run into that, another term is an exhaustive search. Which basically means you have to try every possible combination of values in order to try everything to find out if any of them come up with the right answer you want. A classic problem state it in the classic statement of the traveling salesman. Sometimes people change it, update it to the traveling salesperson. Maybe saying the old usage, not be intending to be exclusive, but that's where they started it. So what is that problem? That problem is you have a graph of cities and they have routes among them, and they have weightings on that. And your problem is to find the minimum cost circuit all vertices visiting each only once. So the idea was a person who had to visit all of the locations on their sales route would want to find the minimum cost of going to each of those cities without repeating any city. This turns out to be a factorial class problem. And you kind of have to try all the possibilities in order to determine them. Depends on the number of vertices and how many edges there are. There could be more edges.
What's that? What's that 18 weight?
Oh. Oops. Oh, that already has a 20. Sorry. Throwing weights up there. Oh, 18 went there. Hand waving. So there could be it could be, more strongly connected, but you always have at least two, because you cannot revisit a vertex. It always has at least two edges on each, minimum two edges per vertex that you can enter and exit. Another difficult problem is satisfiability. Let's see, has everybody had discrete math? Was a prerequisite on. So a little bit of your senior level of computer science, a little familiarity with Boolean expressions. Often called 3-sat, it's the satisfiability problem. Well, Boolean variables. We have n Boolean variables and expression, Boolean expression. Something like and this is just for convenience in the format here. The plus is what? Boolean operator. Pluses or, and these are like multiply. Dots in between. So given some expression, Boolean expression, and the question is, can x1 through xn be assigned true or false values? So the expression evaluates to true. Right, so can we satisfy the expression, meaning, and this could go on, can we plug in true false values for each of the variables x1 through xn such that that result of that whole Boolean expression comes out to be true. You could have, right, if both of these are assigned false, then the whole expression would become false. And you could have negations on here as well. You could have that, not that. This is, turns out to be an NP type of problem. And you kind of have to try all the possibilities. You have to look at them individually, right? Your problem becomes, can you set that true, that true, that true? All of the things that are ANDed together have to be set to true. And you could have negation across each. So it is not slam dunk, right? I mean, if you don't have the negations, then you just set everything to true. If you never negate anything inside here, then it would just always be true if everything's true. So have to make it just a little more complicated with the ability to put not signs, not bars on those. So that ends up to be an NP problem. There's no easy way to navigate that and come up with a polynomial solution for it. And in fact, reset means, the 3 means at most you have 3 terms inside the parentheses here. This one has 2, this one has 3. So reset is an NP hard problem. We'll talk about what that means here as we go along. So a question that might come up is,
Why is this clustered into an algorithms class?
no, that wasn't the question. Algorithms will try to solve those issues. We'll see how we get around this. For automata, we simply recognize that there are 2 classes of problems, as far as we can tell, in the theoretical world. In algorithms, we try to cope with those, right, and find ways to come up with solutions that minimize the impact of that. So, which is the desirable kind of solution? P or NP? P looks really good, right? I mean, as n gets larger, polynomial time algorithms will be better time-wise. Okay, so here's the trick question. Is there ever a time when you want to create a problem that is NP in its solution time?
If it can be P,
What's that?
if it can be P.
Yeah, if it can't be P, then you're stuck with, right, you need to find the solution, so you may have to let it run for a long time, right? Is there any kind of a common problem that you deal with on your computer all the time where someone has created an NP type problem for bad guys? Yeah. So encrypting your password so that the whole point of having passwords, right, is they are too difficult to crack, to break into, such that either by the time somebody could get in, either your MasterCard will have expired, or the data will no longer be important to them. So we're talking about taking a decade to crack a password or something like that. So there is a question that is a legitimate question. Are the NP problems, this is saying, is the class of NP problems equal to, or are the P problems a superset of the NP problems? In other words, are there P times solutions for the NP problems that we just haven't found yet? So that's a legitimate question to ask. The problem has been worked for, I'm going to say about 5 or 6 decades. And thus far, this sounds like a pretty solid wall between these. What the objective would be is, if you can find a solution for the NP problems, then first of all, cryptography would go away, which would be a bad thing in general. But all kinds of problems would yield to very fast solutions. And it just seems like the nature of the kind of problems that are over here versus the problems that are over here is such that this is probably the most likely, this is the reality. But it's not quite proven. There's lots of evidence for it. And we'll talk about some of that upcoming. But there is a subset of all the known NP problems. There are some that are classified as NP hard, which is, in the very literal sense, is meant to say these problems are as hard as problems get in terms of how much time it takes to solve them. If you could solve any NP hard problem, here's a key idea to take away. if you find a P time solution to any NP hard problem, you can solve them all. And in fact, there is no real barrier between them. So problems like, well, a real one that has come with the world of the internet. Once upon a time, children, before you were born, there's no such thing as the internet. And there's no such thing as that stealing identities to speak of. There's also no way to order something and have Amazon drop it at your door tomorrow.
Oh my gosh.
How did they live? How did those people live? Yeah, it was tough. It was right along with the. You know how hard it is to shoot down a pterodactyl with a spear?
Sounds like good old days.
Yeah, that's right. That's right. Where should we go? So it's always fun to watch those spy movies, right? The high-tech spy movies where they have to break into the bad guy's office and sneak under the laser beams and get past the guys at the door with the machine guns and somehow have the bad guy pick up a glass and then steal his fingerprint so we can get through the fingerprint reader and get his somehow scan his retina. And when you get all done, you get into the office where the laptop is just sitting there open. And we quickly slide in the thumb drive and run our special code. And we break into his high-tech security system in minutes. Fortunately, just before we're discovered, and we can, while the last characters of the secret data are being copied to our thumb drive, we can grab it, we can jump out the window, and it's really convenient to have, number one, you probably wouldn't leave your secret laptop with all of that information quite so readily available. But then it's a good thing you had a solution to this problem, which you could, rather than stealing that data, you probably do better selling that algorithm. You do way better. If you're that kind of a computing genius, go straight, make the, leave your life of crime and just write programs, become the next, you don't want to become him, but the next big software person. Okay, so there, in our best estimate, there's a real live fence a wall between problems that we can solve in reasonable time and problems that do not offer an easy solution. Should pull in the one more idea about NP-hard problems, and that is we'll pull up the notion of reducibility. Okay, problem A. Here. So we said problem A is reducible to problem B if we can apply some kind of a transformation as necessary in polynomial time. We can make the inputs to A workable with B, right? So if we have to reformat our input or whatever, so that B will accept it, right? So that seems reasonable. And then, and B's outputs can be transferred back to a solution, right? And the solution to B actually solves A for us, or works to solve A substantially. So it's the idea that we have a problem A something like they have something like so, and we can B solution and potentially transform and basically we can get a solution then for A. the repeat from algorithms. But, good example. If the problem A is to find the median of an unsorted array, median is what? The middle value, right? So if the array were sorted, all we'd have to do is look at the middle element, divide n by 2, and if n is odd, we're already there. If n is even, then you actually average the two values on either side of the middle. Well, can we think of a way to, I just want the median. I want to give it an array of unsorted values, and I want back the median of these, the median of this data is 23.6. Well, let's see, can I reduce the problem of finding the median to something else I know? How about sorting? I can throw in a sort algorithm. So my problem A would be find the median, and my problem B is to sort the array A. So then my transformation looks like, well, you give me an array as my input, and you just want out the median. Put in A, what do I have to do to transform it? Well, probably nothing. It's just an array. I send that array into my existing solution, which is a sort algorithm, fast sort algorithm. When I get all done, what's my transform of the output? Well, I don't want that whole array, so in the array is now sorted, and what I want to do is in constant time, I'll just look to the middle. Where's the middle element of that array? And that gives me my answer. So transforming it is just reading the middle value and sending it out. So the idea about reduction, right? So we can reduce one problem into another problem. And so the last idea here, we'll finish up with so NP-hard problems are what? They're a class of problems. And every NP-hard problem is p-time reducible to let's say let's reduce. Come on, reduce any NP-hard so it's kind of a sidelight. So that's why NP-hard problems as a class become important, because if you can solve any one of them, you can in polynomial time. If you found a solution for one NP-hard problem, you think of them as these are the hardest problems, and if you can find a polynomial time solution for any one of them, then you can solve them all by simply first apply your p-time reduction to get it to 3-sat, and then if you had the solution for 3-sat, you could solve everything else by reduce it to 3-sat and then solve the 3-sat, and then if you had to, p-time transformation back to get the results that you wanted. All right, I think we will stop there. This is chapter 5. Touches on this. We'll look at the post-correspondence problem next time. That's 5.2. And we're looking at, I'll touch on that for a little bit. So 5.2, and then hit the highlights of chapter 7. I think that's going to be our, that's going to be the extent of where we get to. So chapter 7 will be the, we're not going to spend time in chapter 6. So we'll finish off 5.2 and then chapter 7. We have 2 more class periods followed by a review class period before we get to finals week. So we'll squeeze it in there. I will get, like we did before, there'll be a review sheet. Just to recap the final, people always ask how cumulative, is it cumulative? And I usually say, and it's usually accurate, that it's about around 20% would be cumulative of stuff from earlier in the class, but it'll be the most obvious kinds of things that we did. So not stressing detail. Should be able to show, work with a DFA or make a simple DFA for a language or an NFA, a couple of those kinds of things. But the bulk of it will be on the last stuff that we've been covering. And I'll have a review sheet that includes what you should look for from on the cumulative part as well. So shouldn't be any surprises. All right, we'll see you next time. Hi.
So I had a quick question.
Yeah.
Are you going to take a look at the other homework?
Yeah. Yep. I was just thinking about that today as well.
Thank you.
And I will